the recording here. So in this webinar, what I wanted to do was to take some questions from people who've been using ExoLab for a while, and Nita Forsyth, one of our teachers, brought some questions that we'll get to during the webinar. But I really wanted during this webinar to talk about publishing your class data on the community page. We've just actually loaded a new protocol for publishing class data, and so this webinar will show you how to do that. And as an example, we'll publish the WASP 43 data that we constructed together back at the end of March, and then we'll actually try a live. We'll try and have a couple of you share your screen and see if you can do it well. And then I want to also talk about some tools on your teacher manage page that allow you to look at student work. So those are our topics today. And so let's start first with publishing your class data on the community page. And I'm going to click on that community page, which, and I guess I'm going to try to think a little. There we go, so you can see the whole thing. And you'll notice when you get there, there's a list of all of our stars and then a list of schools. Now I will say at this point, if you do not see your school here, this is a new ExoLab community page on which we've pulled over some schools, but not the entire list of schools who in the previous years had published. So if you do want to look at that previous community page, all you have to do is up in the URL bar. So I think if you stick a 1 after the word index, yeah, then you get to this much longer list of schools. And so in this old version of the community page, when you would click on a star, let's say hat P3, you would see all the data in this tiny little box over here, and all the schools who had submitted their light curves listed here. But you'll notice that the relative brightness is kind of that raw value of the ratio of the target star to those comparison stars, which for most of you is different for every star. So if I choose Happy 25, I'm in this range, and you can see that Sauhegan School transit is kind of shifted in a totally different realm from the transit that we did of the same star. So this can happen when we switch out telescopes, and telescopes have different sensitivities, or if we choose to change a comparison star. So what we've done in the new community page is, and I'm gonna get rid of that 1 now, is to create a publishing protocol where you normalize the baseline of your light curve. And I'm going to demonstrate that for you. So when you go to the community page, again, let's pick Hat P3. And instead of appearing in this little box, it appears up here. And you'll see that all the data, all these data sets, and Jim, we have 2 Milton Academies, because once you you registered using capital M&A and once using little M&A. So anyway, but you see that they're all normalized to have the baseline when there's no transit at 1. So you can more easily see the percent dip that we're getting, and so that you can compare apples to apples for all the different stars.
Oh, wow.
Okay. The other thing you notice is as I go over each data set, there's comments that you as a class will be able to publish. And I'll show you how to do that. We put in, since you didn't do this, Jim, we put in republish transit. So we drag this over. So if I want to go back, these are the two control. You can search again by school name or by star name. And so the nice thing about normalizing all these is you can compare how each of these transits has very different kinds of, there's one, we clearly need a new Cotter 1. So those of you who do Cotter 1, we need to publish better data. And so you can see that the Cotter 2 transit is much different than, say, the HAT P36, which is a little shallower. Anyway, all right. So how do you use this publishing tool? In order to do that, this can only be done by the teacher of a class. So our recommendation is that when your class, you've done the whole lab and you feel like you've got a good transit that's worthy of, or even not worthy, you want to get it here publicly, although we'd appreciate better data sets rather than the really messy ones. You, the teacher, go to the publish page here. And you'll have a list, a pull-down list of all the stars you and your class have done, and you'll see that I'm in our Science Education Department account, so I have a lot of stars that we've done. But one of the ones that I did was WASP 43, and actually we did it in our own account, and you guys did it in the workshop account, Teacher 123. So I'm going to choose that, and you'll see that it says pending. To publish a star's data to the community, you need to first use Data Lab Section 5 to identify this star's baseline, dip line. I'm not sure in coordinates, but what it means by that is you need to use the transit modeling tool. So as a class, or you as the teacher, before we even allow you to publish, you have to have gone to the data lab. And for the star you want to publish, which is WASP 43 on March 28th, there is our light curve. You have to go to page 5, which is where that transit modeling tool is. And you want to get the best model. You'll remember in the last webinar, we demonstrated this transit modeling tool. And so you, the teacher, have to have done this. And our recommendation is to do it with your class. And as a review, this is something each of your students should have done. And so I'm trying to find here what's my best score so far. I'm getting a little better here. Let's see. It's a little better. I don't know, this seems more pointy. Yep. Okay, so this is a more tilted light curve. And not getting any better than that. So let's reset to best. Okay. So what I'm doing here is I'm setting the baseline at 1.174, the dip level at 1.131. And then as a class, the way you get your class comments about your light curve data is you, the teacher, put those comments in this box, right? In this box. So this is our class data for WASP 43 on March 28, 2017. We definitely think we detected the transit here, and our calculations suggested the size of this planet is, let's see, that's about a 4% dip. It's probably, I'm not going to do the math right now, but I think that's about a 0.14 ratio, 0.14 times the size, maybe one of you is doing this out there, of its star. Okay. In order for this to get to that community page, you, the teacher, have to click Save Work down here. So I'm clicking Save, and I see the status. My work has been saved to the findings page. So this can be kind of a group discussion with your class. What do we want to say about our light curve? What did we find? Anything we want to be on that community page? Then go back to the Publish page. Now I'll select WASP 43. Oops, why is it not allowing? Okay. So now you notice it has those two values for the baseline and dip line here. It has 1.174, 1.131, and it has a button because it knows, right? The software knows that you, the teacher, have gone and used the transit modeling tool to set the baseline and dip. So if I click Publish, my WASP 43 class data has been submitted. So now we'll go back to the community page. All right, and I'm going to go find WASP 43. Here it is. All right, and here it is. This is our class data for WASP 43. We definitely think we detected the transit here, and our calculations suggest the size is 0.14. And you see that the data is normalized to 1. It's not at that 1.17 or wherever it was in the data lab, so that you can compare it. And WASP 43 is a great example because it's got a pretty deep transit, and it's got that tilted orbit, so it's kind of a triangular shaped dip. So all those things would be things that you could comment on in your comments. Are there any questions about this at the moment?
Yeah, I had one question. You did put the planet size in the box above the comments, and then when you published, so then the planet size was 0. But where's the data come up? Like after you publish it, is the summary, are those 3 numbers listed, like your baseline, your dip, and your planet size?
Yeah. If I go back to WASP 43 here, if I go back to my findings, this page, the my findings page,
okay,
for this star,
right.
I'm not sure if this is a default or this is a prior time when I filled this in. If I go, let me go back to page 5. Again, I didn't, you're right, I didn't fill it in then,
Yeah.
0.14. And now I'm a little worried that if I save this, I'll get rid of my comments, but I think those comments are still in there. Let's find out.
Uh-oh.
We'll find out here, actually, but I don't want to save that baseline. I want to get
I
back.
can see you're experimental.
I'm experimenting right now with this new tool, exactly. So it was kind of in this realm, right? It looks pretty close to what we had before. There's 0.14. I'm not going to rewrite here, and we'll see if I get any, if suddenly on the community page I've lost my published comments. So let's save work. Okay. This is your work. So here's the My Findings page. So here's that 0.14. And at least here, oh, there's different.
It's a different comment.
There's different comments, yeah. The duration and timing also agrees with astronomers. Ah, this is interesting. Planet's orbit appears tilted. So, WAS 43 on March 28. Well, let's go to publish and see if that 0.14 is in there. All right, so this time that's in there.
Yeah.
Now let's, if I update, so I can update published results, but if I update, will I get rid of my comments? Let's find out.
Oh.
Update. Go to the lab. This, okay, so WAS 43. And no comment. Okay. So I just blitzed out the comments that I had written by updating, but I could have revised them. Great, thank you for asking that. That's great. So,
you're thanking me for messing you up? Okay, you're welcome.
yeah, it's all right. But in fact, I'd like to actually do a live demo. This is a little risky, but Jim, I'm going to ask you to sign in to your, before we switch the share, I want you to sign in to your ExoLab page.
I know
you're there, and I know I'm going to stop my share and have you start yours. And Jim is going to share his class data, try the publishing, and we're going to see how it works for him. Although he's share screened down at the bottom there.
Oh, you don't see it yet?
No, we're not seeing your screen share.
Share computer sound.
You want to put desktop. There we go.
Are you seeing me now?
Yeah, yeah.
Okay. Here's Cutter 1, which you wanted data for.
Ah.
So I was never in as good as this as the students are.
I want to note the best scores that Jim is getting are in the 13,000s, whereas mine were in the 3,000s. So that's telling us, you see all these dots at the bottom that indicate students might have been measuring the wrong star.
Yeah, all these down here, you mean?
All those down there and at the top.
Yeah.
Nonetheless, you do have an overall trend that we ought to be able to optimize here. So, but you can see your uncertainty is a little big too in terms of 0.05. But still.
Okay.
You like that?
Sure.
Okay. Yikes. Okay. So you need to, big. Okay. Do you want to publish to the world the comment that says big? All right, fine. So you
That's 0.06. Well, I can't do the math in my head, but that's still a very large percentage.
well, it's 0.04, right? Because look at the right side. It's 4%.
Oh, I didn't even notice. Yeah, so 4%. So that's 20%. So, right, square root of.
Very big, roughly. Okay, so now if you scroll down, okay, so,
I'm scrolling down.
and hit save work.
Yes.
All right, so now let's go publish.
To publish.
Mhm.
Coder 1, pending. Publish results. Publish.
Okay, so now let's go look at the community page. And remember, we had one Cotter one that was not great, and now we have yours. Uh-oh. Oh, was this for Johns Hopkins? Is this your
Yes.
okay. So if you highlight your school, there's your data.
Okay.
Okay. So clearly in this this particular star, we haven't yet really gotten enough data to define where that is, and I'm not sure the Sauhegan data probably is some data we shouldn't have pulled over. I'm not sure.
It doesn't look very wide in time.
Yeah, yeah. So anyway,
So
you've now seen, I'm now going to ask you to stop your sharing, and I'm going to.
what is the min average?
Yep. So the red dots are kind of the previous half hour of data bin. So that I'll share mine now. Yeah. So you could see with WASP 43, you're starting to get a little bit of more of an average of all the data. And the more data that gets published, the kind of more well-defined that average will be. I think Roy was thinking of adding a potential show or hide binned average. I don't know whether you think that would be useful or not. Any thoughts on that? Okay. So that's what the red dots are. Those are the actually they must have.
So this shows data of the relative brightness that different people have measured, but you also have plots of what the average, or what the variation was in the size of the planet that was calculated, and the baseline value, or.
Yeah. Okay. So so now I want to get to some questions that Maida had brought up with regard to interpreting these light curves. So in the data lab, we kind of have you interpret the size of these planets, assuming that the target star is roughly sun-like and sun-sized. So that when you get to pages 8 and 9, here we have a duration that's, you know, roughly, I don't know, 1 hour, hour and a half, an hour and 45 minutes, right? And then we have a percent dip that's about 3.5%, and so you do the square root of that to have the size of this in comparison to its star. But if its star is not the size of the sun, and you get a value of 0.2, but it's a smaller star, then in fact the actual size of the planet is not twice the size of Jupiter, but some factor smaller, by the same factor that the star is smaller than the sun. Does that make sense? So Maida, to answer your question, the question that Sam asked, we can tell we have stars. You're right, the spectra of stars are a general indicator of how big they are. Bigger stars are brighter, they have different lines in their spectra, and so the cooler stars are generally smaller. And so from the spectra, you can tell the approximate size of the star. And so you can still read off the relative size of the planet that's transiting compared to its star. You know the ratio, but the actual size compared to Jupiter depends on the actual size of the star compared to our sun, right?
Yeah, that makes sense.
Yeah. And in fact, on the ExoLab course, and this is, I demonstrated this a couple webinars ago, we've added the index of ExoLab target planets. I'm going to go look at that right now. And here is WASP-43, which we were just looking at. And I'm going to look at the actual professional database for WASP-43. And a couple things you're going to notice here is the where is it here? I think I have the star. Okay, the radius of this star compared to the sun is only 0.6. This is a small star. So while we got the result of 0.14 Jupiter sizes, or maybe larger, that was a 3% dip, you can see that the professionals took into account that this was a smaller star. So in fact, that WASP-43b is a little smaller than Jupiter.
Okay.
Right?
Mm-hmm.
So, if you knew the actual size of the star, then your ratio would still work to tell you, you know, you could then kind of use that number compared to the sun to scale up or down your comparison with Jupiter.
Yeah, I think this would be more of like on the wrap-up day as opposed to, because I think otherwise the kids are just going to get confused.
Exactly. So, and in the lab, you'll remember that on page 6, there's this model, and I'm going to hit Z to stop that orbiting star. I just hit Z, right? And that this dip basically is a direct indication of the radius of the planet compared to its star.
Yeah.
Okay. All right, and I noticed that the Jim, the commentary on the side is really important here in terms of the professional findings are really done the exact same way your students are doing theirs, and they have to take account of the accuracy of their instruments as well. So it's not clear that you want to use this as a determiner of whether kids have found the right answer, but sometimes after because their result is their result, and but you can use it to as a reflection on are there strategies they could use to improve their uncertainties. Okay. All right. I want to note that I added a few things to the ExoLab educators community that you should be aware of, and that includes, again, that index. I'll be adding some more links to some NASA exoplanet data and visualizations. And one of the links I didn't have time to add, Mita answers your third question.
Yay!
Which is, how do they detect multiple planets? And I'm actually just going to I'm going to do a Google right now to show you this, because TRAPPIST-1, okay, because there is a great video on, oh, that's not it. Let's see. NASA reveals. Yes, this is it here. Here it is. So, and I will put a direct link to this, but let me see if I can show you this image of the actual data from the Spitzer Telescope. And do you see all these dips?
Yeah.
Each of these is a different planet, and you can see they've identified it. So here's the periodic dip of planet B, which is an inner planet. It's happening much faster. Here's the periodic dip of planet D, which is further out. So in the same period of time, you only get 3 of those going by. And so clearly each of these dips, if you stretched out this graph, they'd look just like ours, right? Because this is in terms of days rather than hours. So does this make sense, Mita?
Yeah, this is great. This is exactly what I'm going to show them when they, tomorrow.
Yeah, and it takes some time to parse out. You see that some of these are like this one, D. You see how it's much less deep? See, there's the D dip too. It doesn't go as deep. Can you see that? Whereas this one's way down here.
Mm-hmm.
So that's an indicator of the size of that planet, right?
Yeah.
This one's a bigger one. This one's a littler one.
Mm-hmm.
And so this is the raw data. And from that raw data, the visualization staff actually created, you can see D, we saw the D dip, and I was looking at the B dip, I think, and see it's about half the size,
Mm-hmm.
right? And if you looked at that, that data, you could see it was half the dip. Or actually, wait, have I got that right? No,
I think it's a,
it's the square effect has to take into there. Yeah, so that's how you find multiple planets. And then with regard to your third question, Mita, about, you know, doesn't this size depend on how close the planet is to its star? So as my finger is moving closer and further away from the camera, if you're looking at, I'm covering more and less, but that's because the camera is only,
yeah.
a few inches from my finger and fist, but now put my finger and fist a light year away, and this isn't going to make a difference.
Yeah.
Right? So the relative size of the planet, the relative distance of the planet and its star are the same compared to the telescope that's viewing the change in dip. Okay.
Thank you.
So the last thing I wanted to get to today was looking at student work, because each time, for example, on this page in particular, if I reload it here, I'm having trouble grabbing that, but let me reload. So on this page that says, how small a planet can I confidently detect with this system, right? You can see that if you had, actually, let me get back here. So if I had a dip that was 1% or less, given this noise, that would be hard to detect. So a student might write that. It seems like this telescope could only detect a Jupiter-sized planet or larger. And okay, so they save their work. You have a few options for examining what your students have entered in all these various labs where they have the opportunity to say something. So in the modeling lab on pages 3 and 5, they enter comments. In the image lab, when they are graphing brightness on, where is it? On the My Analysis page, they have the opportunity to enter comments. And so you could log in as each student, if you knew their password, go to each page and examine, but we've tried to provide you with a tool under the Manage page, and it's this journal tool. And so under the journal tool, each lab, if I click on it, has student comments. And here I have, you can see that student comments. I should mention for the modeling lab, anytime a student would update their comments, it only gets saved the last time they entered. And you can either print that directly or you can download all your student comments as an Excel spreadsheet. In the image lab, you'll notice that the comments are associated with a particular star, because you may have students doing many stars and doing an analysis of each of those stars. And so for each student, you have the stars that they have analyzed in ImageLab, and here's the number of stars they've actually made measurements of. Frank's been pretty active in here. And on Cotter 2, he actually made some comments. And again, on Trez 3, I did some points, made some comments, and you can download this as an Excel spreadsheet so you can see what your students' comments were. And similarly, in Data Lab, there's several places where students enter comments, and it's by star again. So Erica, for her HAT P10, filled in everything, but for her WASP 77, she didn't do anything. And Frank, again, has been doing several stars, and you can see what he did for that, and you can then download as an Excel spreadsheet. So this is a way you can keep track of student work. Are there any questions about that? Great. I guess the last thing I want to do is in the, again, back in the ExoLab educators community, note that I've also added some community contributed resources here.
Oh.
And so, Mita, all those nice sheets that you've done are actually here now. And if there's any you want taken off, we can definitely do that. I should note that many of these sheets are based on earlier versions of the ExoLab. So as you look at them, in one of the first webinars and on the online discussion boards, I think Scott in particular, you had asked for a place to share people's scaffolding that they use for their students. And so we've collected a few of those things here, and I urge you to examine them. And Jim, for example, had this when he was on a sabbatical with us, I believe. Oh, I'm not on my computer. This is just really
just exit.
Just exit.
It'll open.
It'll open. Okay. Really?
Mm-hmm. You don't want to sign in.
I don't want to sign in. Not on my computer. I'm on our programmer's computer, and of course he never uses Microsoft Word, so sorry about that. We also have a page of, and Martin's on the line here, resources from Martin, who's been collaborating with us and has been downloading. He posted on some of the discussion boards some of his transit data from microobservatory images. He ends up downloading the entire set of FITS images and using a third-party software. And Martin, if you want to just say a couple of words about it here, and I think we're going to have another atlas from you as well.
Yeah, sure. Hi, everybody. I'm over in the UK. It's a bit dark here now. I've been working using the microobservatory data for the past 6 years or so, but only recently looking at the exoplanets. So as Mary's just mentioned, I download the individual FITS files, and then I put them through a freeware program called UniWin, which allows me to actually identify all the stars on the image and then produce a light curve of a particular target. Mary's kindly put up the tutorial as I went through with them a month ago, and that's quite detailed. If anybody wants to know any more, just get in contact with me. The other thing is, as Mary's mentioned, I'm building up an atlas, or I'll probably actually call it an ensemble or a corpus of light curves. I don't know whether you can switch over to my screen. I can just show what's on it.
Yes. Let me stop the share here, and you can start a share, Martin. And Roger, I'll answer your question about a FITS file while Martin is doing this. The microobservatory telescopes, the format of the file is called FITS file. That's what astronomical file format. And while our online lab loads the FITS files for you, there's an archive that you can get that's linked to from the main microobservatory page, and maybe I'll put it in the ExoLab community as well. I'll show it to you after Martin's done, where every night the 100 images that end up in your ExoLab account are also available for anyone to download and use.
It's the full field of view of the telescope?
It is. It's the full field of view of the telescope. It has. It does have a header. It's basically there's yeah, it is a file that's basically the XY values and pixel values of every spot in the detector, but at the front of it is a header that tells you where the telescope was located, what time the image was taken, the Julian date, the altitude the telescope was pointing, all kinds of metadata like that.
Thank you.
So somehow we have Roger sharing a screen. Is that right? No, you're sharing. What's happening, Martin? If you specify desktop, there you go.
You've got this. Okay.
Great.
So this is Atlas is the wrong word, but it's a work in progress. But I've currently gone through around about 7 transits. And if we go to WASP 43, I now go to screen mode. You can see this is the light curve that I've extracted. So I take all the FITS files, put them through MuniWin, which gives me a text file. I then take that text file and put it through an Excel spreadsheet just to tidy up some of the data, because as you've seen, it's quite noisy. I then take a text file from that and input it into the Czech Astronomical Society's exoplanet transit database, which allows you to actually model the actual transit against your data. And the output you see on the left-hand side here, this is the light curve. You get 2 versions, one which is detrended, because sometimes you'll find that the baseline is at an angle, or is maybe
actually, Martin, could you go to one of the earlier stars that shows that more?
Yeah. Let's have a look.
There you go.
There's one that's going down. As you can see, it is quite noisy. These are quite noisy. That's a reasonable one. Here's one that's going up and slightly down, again going up. So you can actually take that into account. Let's go back to WASP 43. From that, you can then publish it to a site called Tresca, which is Czech for something. I just don't know what it means, but it's the queue for the people in the Czech Republic to actually review your light curve and then publish it to their exoplanet transit database. What you get is quite a lot of detail about it. It works out for you the radius of the planet, the inclination, And as you can see here, this is WASP 43. And as on the animation, it's grazing, so the angle is about 80 degrees compared with 90.
And you remember our ExoLab WASP 43, we commented on how kind of pointed, and you could see in Martin's smooth model that it doesn't stay at the dip for a long period at all.
Yeah. So say the transit's about 68.7 minutes, so just over an hour. The other thing you can do is then compare, once you've published it to Tresca, you can then compare your observation, which is the blue, with other people's observations. And you get a number of, there are 3 plots that are provided. Probably the easiest is to start at the bottom. So this is the depth of the transit. So it just plots out that. This is the duration, and you may be able to see there is actually a dotted line that goes across, which is what the published value is. But the other one is this O minus C plot, which is the observed midpoint of the transit compared with the calculated midpoint based on the in this case it's the discoverer's view of what the period and the actual date on which they discovered it, and you can then compare how your plot, your estimate of the midpoint compares. And again, that's another, going back to what was I think it was Mita was saying about detecting other planets. This is one way that you can actually detect whether there are other planets in the system, because as the planets orbit, another planet that you may not be transiting, that you do not know about, could actually be perturbing the orbit of the planet you're looking at. You get what are called transit time variations. I don't think, from looking at the data so far, whether we can actually use the microobservatory to get TTVs of other planets. I don't think it's that accurate enough. One thing that I have done is that I've got around about 25 transits of HAPP 32b, which I'm currently still working through and will eventually publish to give a baseline of what the capability of microobservatory is. That's pretty about it.
That's great, Martin. I want to point out a couple of things about, one is we are working actually both with the people at the NASA Exoplanet Archive and with Martin about the possibility of creating a way so that you can export your students' data into a file that is acceptable in the same way that after Martin uses this MuniWin software, the data is in a format that the Czech database can accept. And so a lot of what Martin's doing is helping us understand what are the parameters, you know, how do we need to, what additional elements do we need to add to the raw values that the students are creating. And you'll see that the Czech database, in the online ExoLab, we use the most simplified model, which is the straight line, baseline, 2 ingresses, and the bottom. But the Czech Tresca modeling tool is a little more sophisticated. You can see that it accommodates for this idea that WASP, that it's a disk crossing in front of a disk, so that the bottom of the transit is rounded. And it also, that detrending accommodates the fact that the telescope is looking through an atmosphere, and so it's taking account of that as well. So let's.
Yeah.
Okay. I think that was kind of the things we wanted to cover today. We want to make sure you know how to publish your data with your students to our community database. As we go into the future, we hope to have more opportunities to possibly even submit that data to other archives like the Czech and the NASA Exoplanet Archive. We'll be adding some more resources specifically related to some of the things we talked about here. Mita, for example, I'll make sure that TRAPPIST visualization of the multi-planet system that was discovered just in February is also in the resources on the educator's website. This webinar kind of formally ends the series of webinars for this spring, but we will continue to monitor the online community, and we will from time to time announce webinar opportunities with scientists. We actually have a recent PhD student who did a great presentation of his thesis, an overview of Kepler. We're going to put his video of his thesis defense on the community here, but he's agreed to have an interactive Q&A session sometime soon. So we'll have these opportunities. We'll always record them. And we also want you to know, as ExoLab community members, if you have specific issues at any time, you should use the online discussion forums or email us directly. It's better if you use the online forum because then we can answer everybody at once. And we'll, especially as you're starting to actually implement the lab with students. So Brian, when you're doing your summer online course, as things happen, be sure to keep in touch with us. And as people have insight from teaching it that they want to post back on the ExoLab community, we really, again, appreciate all those community contributed. And again, Jim, to answer your question, the things that people submitted were submitted during the field testing. And of course, you submitted yours. So my understanding was they were for sharing with people, and that's the ones I posted. As you all have more to share about how you experienced it, it'll really improve the lab for everybody. So anyway, thanks to everyone. Keep in touch with us. We'll be providing more opportunities for further live webinars and learning, but the educators community is open for online discussion as well. All right. Stop.